A town can sit outside the white hurricane cone and still take damaging wind, deep water, and a day of hard rain. Another town can sit inside the cone and never see the center. Those outcomes sound like a broken forecast, only if the map is answering a question it was never built to answer. Most of us read the cone as the shape of the storm. The wide end looks like the hurricane is growing. The boundary looks like danger stops there. The center line looks like a promised route. Every part of that reading feels natural, and nearly every part is wrong. So what is the cone measuring? Why does it widen with time? Why can severe weather reach far outside it? And why is the National Hurricane Center testing a different cone in 2026, built from ellipses instead of circles? The trap is visual. One white shape carries a forecast line, timestamps, intensity letters, coastal warnings, and sometimes the current wind field. Our eyes fuse those layers into one object. The cone then becomes a general danger map, even though its geometry describes only one uncertainty. Picture two markers near the coast. One sits just beyond the white edge, but beneath the storm's broad right-hand wind field. The other sits inside the cone on the quieter side. If we judge both places by cone membership alone, we rank their local wind risk backward before the storm even arrives. That uncertainty belongs to the storm's center, not its cloud shield, not its rain, not its surge. The center is a moving point inside a weather system that may span hundreds of miles, and the cone records how wrong forecasts of that point have been in the past. We will build the cone from those past errors, pull apart speed error from direction error, and compare the operational graphic with the 2026 experiment. Then we will rebuild the advisory as a stack of maps, each answering one question the cone cannot. Forecasters first estimate the center from satellite imagery, aircraft reconnaissance, radar, and surface observations. That fix has its own uncertainty, especially when a cyclone is disorganized. Still, the advisory needs one present position and a sequence of future center positions. Connect those forecast positions and you get the familiar track line. The dots usually sit at 12-hour intervals through day 3, then longer intervals through day 5. Letters inside the dots describe the forecast cyclone state or wind category at that time. None of that tells you the width of the storm. A compact hurricane and a sprawling hurricane can receive the same track cone when they are in the same basin and season. Their wind fields can be radically different even if their forecast center lines overlap. Storms are not neat circles either. Wind can extend farther on one side because the cyclone's rotation combines with its forward motion. Dry air, shear, fronts, and land interaction can push rain or strong winds into lopsided shapes that cross the cone boundary. After the storm, analysts reconstruct a best track from all available evidence. That record can differ from positions issued in real time because later aircraft data, radar, satellite analysis, and surface reports sharpen the center estimate. Forecast error is measured against that post-storm track, not against an infallible live dot. Now separate the two layers. The center travels along a forecast path. Around it, a broad and changing hazard field travels too. The cone follows uncertainty in the first layer. Wind, rain, waves, and surge belong to the second. This distinction is the hinge for the whole graphic. Once the storm becomes a point, the cone can be constructed with geometry. The surprising part is that the width does not begin with today's model spread. It begins with several years of forecast misses. Take every official Atlantic track forecast from the previous 5 years. At each lead time, compare the forecast center with the later best estimate of where the center actually was. The distance between them is one absolute track error. At 24 hours, those misses form a cloud around the forecast point. Sort the distances from smallest to largest. The operational radius is chosen so that roughly 2/3 of the historical errors fall inside the circle and 1/3 fall outside. Repeat that calculation at 12, 24, 36, 48, 60, 72, 96, and 120 hours. Short forecasts have smaller error circles. Long forecasts have larger circles because small mistakes in steering and speed have more time to accumulate. For the 2026 Atlantic season, those radii begin at 25 nautical miles at 12 hours and reach 200 nautical miles at 120 hours. They come from official errors during 2021 through 2025. Next season, the 5-year sample rolls forward, and the radii can change. Put those distances on one map. The 12-hour circle is small enough to fit around a metropolitan area. The 5-day circle can span a large part of a coastline. What grows between them is accumulated position error. The physical hurricane could expand, contract, strengthen or weaken independently beneath those circles. Place each circle on its forecast point. Now sweep a smooth outer boundary around the circles. The familiar cone appears. It is not drawn by stretching one triangle from the storm. It is the envelope of several separate historical error circles. The wide end now has a precise meaning. It shows that the center forecast is usually less accurate farther into the future. It does not show the hurricane expanding, intensifying, or becoming more dangerous with every hour. Imagine two storms on the same day. For one, the major models cluster tightly. For the other, they split toward different coastlines. The operational cone radii at each lead time are still the same because both graphics use the same seasonal table of historical errors. Model guidance still matters. Forecasters use it, along with observations and physical reasoning, to draw the official center track. A messy ensemble can lower confidence in that line. It simply does not make the operational cone automatically balloon around that particular forecast. If new observations move the estimated center or reveal a stronger ridge, the next official line may shift. The whole cone moves with that line, but its lead time radii come from the same seasonal table. A forecast update can therefore relocate the corridor without changing the rule that sets its width. The cone is closer to an average error allowance than a live confidence envelope. It says how large official track errors have tended to be at each forecast hour across many storms. A single forecast can be more predictable or less predictable than that historical average. This creates a strange visual mismatch. A clean, narrow cone may look confident even when the steering pattern is fragile. A broad late cone may look vague even when nearly every model agrees on the same general corridor. The shape alone cannot tell you why uncertainty exists. That is one reason the forecast discussion matters. Forecasters describe ridges, troughs, model disagreement, center relocations, and timing problems in words. The cone compresses years of track performance into one boundary, while the discussion explains the current storm. Put the model tracks behind the cone, and the roles separate. The models supply possible solutions. Forecasters choose the official black line, and the cone wraps recent official error around it. The layers work together without measuring the same thing. At one forecast hour, an operational circle is sized so that about 67% of historical official center errors were smaller than its radius. That is a statement about a collection of past forecasts, not a customized probability for every town under the white shading. The white area is not uniformly likely, the center line is not guaranteed, and the edge is not a cliff where probability suddenly falls to zero. The graphic does not assign a location-specific center probability to every pixel inside and outside the boundary. There is another subtlety. Hitting the circle at one forecast time is easier than keeping an entire 5-day path inside every part of the cone. NHC says the complete center track remains within the operational cone roughly 60 to 70% of the time. Think of the center passing through a row of gates. It may fall inside the 24-hour circle, inside again at 48 hours, then slip beyond the 72-hour boundary before returning. The final path is one connected history, while each radius was calibrated from errors at its own forecast time. That leaves real tracks outside. A center crossing the boundary does not prove that forecasters failed in some extraordinary way. The cone is deliberately built from a percentile, and a meaningful fraction of historical errors lies beyond it by construction. The reverse mistake matters too. Being inside the cone does not mean the center will pass directly overhead. The cone contains many possible center positions across time, and a city near one side may never be close to the final track. Replace the white fill with the hidden error samples and the boundary stops looking magical. It is the contour NHC selected through a cloud of past misses. The graphic stays readable because companion products carry the information left outside that contour. Suppose the forecast places the center at 1.72 hours from now. The observed center can miss that target in two basic ways. It can travel too far or not far enough along the expected route, or it can move left or right of that route. The first is a long track error. A storm moving in the forecast direction but arriving early can be far from the forecast dot. So can a storm that slows down and lags behind. On a map, both errors stretch forward and backward along the path. The second is cross-track error. The center bends to one side of the forecast route because the steering pattern differs from what was expected. On a map, those errors spread across the path rather than along it. Draw the total miss as one arrow from forecast point to observed point. Project that arrow onto the forecast direction and you get the along track component. project it across the route, and you get the cross-track component. The same absolute distance can hide very different failures of speed and steering. The operational cone uses circles based on absolute error distance. A circle is simple and familiar, but it treats every direction around the forecast point the same. It does not show whether historical uncertainty was longer along the route or wider across it. Speed error also changes timing. Two tracks can follow nearly the same geographic corridor while reaching a coastline hours apart. A center map can look accurate in space and still be wrong in time, which matters for the arrival of wind and water. Once a long track and cross-track errors are separated, a circle is no longer the only natural shape. An ellipse can stretch with the error components. That is the idea behind the experimental cone appearing beside the operational product in 2026. During the 2026 season, NHC is issuing an experimental cone in addition to the operational graphic. The experiment does not merely redraw the same 67% circles. It changes both the geometry and the probability target. At each forecast point, the experimental method places an ellipse. One axis follows a long track error, and the other follows cross-track error. The axes use the 90th percentile of those error components from the previous 5 years. Smooth those ellipses together, and the experimental cone becomes a likely track area for the center, designed so the center would be expected to remain within each ellipse about 90% of the time. That is a different statistical promise from the operational cone. 90% does not turn the experimental white area into a local hazard probability map. It still concerns center location at forecast lead times. Wind, water, and rain remain separate. The experiment changes how track uncertainty is shaped and communicated, not which physical hazards the cone contains. The two cones can look surprisingly similar in overall size, even though their construction differs. The ellipse can extend farther, where speed errors dominate, and shape the boundary differently where directional errors matter. The operational cone remains available, while NHC collects feedback. This is exactly where careless language causes trouble. A 67% operational error circle and a 90% experimental error ellipse cannot be described as if they were interchangeable. Any screenshot needs a clear label for which graphic and season it represents. Transform the operational circles into experimental ellipse, and the visual change reveals the hidden variables. The long axis can carry timing error, the cross axis can carry directional error, and the 90% target is stated separately from the operational rule. Now put the storm back around its center. Tropical storm force winds may extend far from the eye. Hurricane force winds occupy a smaller area, often with different reach in each quadrant. Rain can be displaced again by shear and the storm's interaction with land. A moving cyclone adds its forward speed to winds on one side and subtracts it on the other. That can make the strongest wind footprint asymmetric. The center can remain inside the cone while damaging wind reaches well outside the white boundary. NHC advisories describe wind radii by quadrant for this reason. The northeast reach of tropical storm force wind can differ sharply from the southwest reach. Put that lopsided field around every plausible center position, and the local wind question becomes much broader than the center corridor. Rain obeys moisture flow, terrain, storm speed, and band training. A distant rain shield can flood places that were never near the forecast center. The cone carries no rainfall amount, and no promise that the dry side will remain dry. Storm surge depends on wind pushing water toward a particular coastline, the storm's size and angle, forward speed, tides, and local bathymetry. A center track alone cannot convert those ingredients into water depth at a specific shoreline. This is why coloring every location outside the cone as safe reverses the map's meaning. The boundary marks 1 percentile of center track error. Hazards can cross it because hazards have size, and the center itself can cross it because the contour never represented certainty. Shrink the storm to a point, and the cone works. Expand the wind, rain, and water layers around that point, and the white boundary disappears inside the larger system. The forecast was not contradicted. We had been asking one graphic to carry 4 forecasts. The cone answers a track question. Where is the center likely to travel, given the historical performance of official forecasts? It is a corridor for the moving center, not a complete local impact forecast. Wind speed probability graphics answer a location question. They combine uncertainty in track, intensity, and wind structure to estimate the chance that sustained winds will meet specific thresholds at individual places during the forecast period. Arrival time graphics answer a clock question. The earliest reasonable version marks the time before which there is no more than a 10% chance of tropical storm force winds beginning. A separate most likely version uses a different risk threshold. Even the wind maps come in thresholds. Tropical storm force, 50 knot, and hurricane force probabilities describe different events. A location can have a high chance of tropical storm force wind and a much lower chance of hurricane force wind. One color or one cone cannot preserve that distinction. Surge products answer a coastal water question. Peak surge forecasts give ranges for sections of coastline, while the potential storm surge flooding map estimates how high water could rise above normally dry ground in specific areas. Rainfall forecasts and excessive rainfall outlooks answer a freshwater question. They depend on storm motion, moisture, terrain, and the larger weather pattern. Their high-risk areas can be shaped very differently from the center cone. Stack the products and the advisory becomes a system instead of one white shape. Center path, wind odds, arrival time, coastal water, and inland rain each occupy their own layer. The maps disagree only when we pretend they are answering the same question. Track forecasts have improved over the long term, so the historical error radii used for the operational cone have generally become smaller. Better forecasts produce a tighter envelope around the official line. That is real progress. But a smaller cone can strengthen the false impression that hazards are confined to a narrow corridor. The center forecast improves while the storm itself remains broad. A clean graphic can look more precise than the impact forecast really is. This is a communication paradox created by success. 20 years of better track forecasts can pull the white boundary inward, yet a large cyclone may still push wind and water across several states. The visual precision of the center track improves faster than our instinct to separate the point from the storm. The cone is recalibrated from a rolling 5-year sample. That keeps the geometry tied to recent forecast performance. But it also means cone width is not a direct measure of a storm's physical size or intensity. A major hurricane does not earn a wider cone simply for being stronger. Track skill and intensity skill are separate problems. Forecasters may place the center well while missing rapid strengthening. They may predict intensity reasonably while the center bends away from the line. One narrow cone cannot summarize both dimensions. NHC has added and tested other layers, including inland watches and warnings, because people need impact information that the center cone never contained. The challenge is not to stuff every hazard into the cone, it is to make the product stack easier to read together. Watch the cone narrow while the wind footprint stays wide. Forecast skill improved, yet the hazard boundary did not collapse with it. The better the center forecast becomes, the more important it is to remember what the white shape excludes. Start with the center track. Note the forecast times, the current position, and how the route changes from one advisory to the next. Treat the cone as uncertainty around that center path, using the definition for the specific operational or experimental graphic. Then move to wind probability and arrival time. These maps translate track, intensity, size, and timing uncertainty into local wind questions. A location outside the cone can still have a meaningful wind probability because the wind field travels around the center. For a coastal location, read the surge watch, peak range, and inundation map. For inland flooding, read rainfall forecasts and excessive rainfall outlooks. The correct map depends on the mechanism that can affect the place. Repeat the stack when a new advisory arrives. The center can relocate. The official line can bend, wind radii can expand, arrival times can shift, surge and rainfall forecasts can change even when the cone appears almost unchanged. Keep the advisory times in order, instead of replacing the old map with the new one. The sequence shows which layer changed. Sometimes the line moves, while the wind field holds. Sometimes the line barely moves while the arrival window advances, and the rainfall maximum shifts inland. Use the forecast discussion to connect those layers. It explains why the track changed, which models disagree, how steering may evolve, and where confidence is limited. The maps show the latest state, while the discussion explains what changed in the atmosphere. One advisory now becomes a 5-panel instrument rather than a single verdict. The cone remains first because center track organizes the storm. It stops being the last map because local consequences require more information. We began with a boundary that looked like the storm. Build it from scratch, and the illusion falls away. Historical center errors become circles. Circles sweep into an operational cone. Along track and cross-track errors become experimental ellipses. The official center line can shift. The white area encloses a calibrated amount of historical track error, and its edge is only a percentile contour. Those distinctions explain how the forecast can remain useful even when the center leaves the cone. Put wind, rain, surge, and timing back around the moving center. Each hazard has its own geometry and uncertainty. Some extend far beyond the center corridor. Others concentrate in a narrow place for reasons the cone cannot show. In 2026, the operational and experimental cones make this logic visible in two forms. One uses 67% absolute error circles. The other tests 90% ellipses split by speed and direction. Both still describe the center. Neither cone can be the final word for a location because neither contains the complete storm. That limitation is not a flaw hidden in the fine print. It is the trade that lets one compact graphic show a 5-day center forecast and a calibrated amount of track uncertainty. The useful question is no longer, am I inside the cone? Ask what uncertainty the map contains, what hazard matters for the location, and which companion product was built to answer that question. The cone stays compact by leaving most of the hurricane out. Read it as a scorecard for forecasting one moving point, then rebuild the storm with the other layers. It stops looking like a fence and starts working as one part of a larger forecast.